This week we don't have quiz, so we postpone to the second last week. Apply the two quiz. The quiz, I think, will be quite close to the exam question. So, yeah. Contain the course information. The quiz content will start from partial ordering up to particular the Hessel diagram. discuss the quiz question also. In previous notes. Anything from you? Any questions from you? Hopefully, we will end the lecture content at week 14, and then week 15, when they do revision or something. I think graph will take a bit longer than 3 weeks, but the last chapter should take less than one lecture. Hopefully, we will end all the content. The week 15, we can do revision. Any question for you about lectures for it? Okay, so let's start today's lectures. So last week we stopped at the Euler formula. So Euler formulas tell us how to compute the number of region bounded by a planar curve. Okay, using the number of edges and vertexes. So first start with a planar graph. So remind you what the planar graph is. It's a graph that has a representation that have no edge crossing. Okay, suppose we have E edges and D vertex and R number of regions. How are we how can we combine these three numbers here? Who can remember the formula? Anyone can remember formula? Yes. So it's equal to R equals to E minus V plus 2. 2 is the Euler characteristic of the planar graph. So you can see that there's okay, since you learn more maths, right? Let me tell you something. So you can see that this one is a vertex is a dot. Okay, edge is a line. Region is some region bounding some area. Okay, so you take a larger dimensional number. Okay, I mean there's an alternating sum here. Okay, so you take two-dimensional stuff minus a one-dimensional stuff and add a smaller zero-dimensional stuff, and then get 2. Okay, this is what this formula does. You take alternate sum, okay, on different dimension, going from high to low. So this is how you remember this formula. Two-dimensional minus one-dimensional add zero-dimensional, plus minus plus alternate. And then you will get this 2. And then today we will go through the proof how to get this 2, number 2 here. So let's see how to get this number 2 here. So we're going to prove it using induction, an inductive proof. So first, consider a planar representation of G. Okay. So turn your graph into a planar representation with no edge crossing. Okay. And then two, you can construct a sequence of subgraph. A sequence subgraph. So G1 out to Gn. So the last one is a G. Okay, maybe I use different GP maybe. GP per G. Okay. So how do you create this subgraph? So in each step you add an extra edge. So how do you do this? So how do you start? So you start by any edge on the of your graph. Okay. So when you add one edge, automatically you will add two vertex. Right? Edge always come with vertex incident to the edge, right? And then and each step you add one edge. Okay. So how to add the edge? The edge that is incident with a vertex in the previous subgraph. Okay. So if in the case that the other vertex of the edge is not in the original graph, then you add that vertex in. Okay, let me draw one example for you to see what is going on here. Okay, this this edge in the previous graph. Yeah. So for example, let's say our G is, let's say our G, for example, let's say our G is something like, yeah. So this is our G. So what's G1? So maybe G1 you can take this edge on the left, top left, okay. And then G2, this one plus another edge, but this point is not in the previous edge, right? So you add a, and then G3, you can do this, and G4, you can add the edge without adding the, and then you keep going. Then you produce a sequence of subgraph, and then in the end you will get back your G. Is it okay? Okay, careful. Okay, okay. So in each step, we want to show that this formula holds. Okay. So we have to start from base case. Is everyone following here? Following? No question? Okay, okay. So next, we have to prove by induction. So we prove R equals to E minus B plus 2 by induction. So what's the base case? So base case is you need to check the G1 case. Okay. G1 is always what? A vertex. Okay. So what's the number of region here? What's the number of region here? Huh? What? What's the number of region here? 1. Okay. So the number of region here is 1 because everything here only one region, right? Okay. So how about H? H is 1. Vertex is 2. Okay. So R equals to E minus B plus 2 is 1 equals to 1 minus 2 plus 2, which is true. Okay. So for G1 case, it is true. Base case is true. So let us assume for inductive hypothesis. hypothesis. Suppose I equals to E minus V plus 2 is true at GK. Okay, so suppose it's true for every step. And then we want to prove for the next step. Okay, that's it. Step. Okay, so we want to show that R equals to E minus plus 2 is true at GK plus 1. Okay, so what's the difference between GK and GK plus 1? What's the difference between GK and GK plus 1? Recall the construction here. What's the difference? Huh? One more edge. Okay, so this means you add one more edge from GK to GK plus 1. Okay, so there are two ways to add this edge, right? Remember, either when you add this edge, the both vertex is already in there, or when you add the edge, you need to add an extra vertex. So there are two cases to check in. Okay, so there are two cases to check. For case one, new edge with new vertex. Case two, new edge with pre-existing. Okay, so the general case is like you got your GK. Can I use got your GK? Okay. Then you add one edge with one extra vertex. Okay, this one example. Okay. And then how about this one? So you already have a pre-existing vertex. You just add one extra GK plus one. Okay, can follow? Up to here. So far, okay? Two cases. Okay, so for these two cases, you need to check that the formula holds as well. So we need to relate what's the R before and after adding. Okay, so RK plus 1 and RK. Okay, so what's the number of region before adding and after adding an edge? Okay, after adding an edge, do you increase your number of region? No, right? Yeah, so RK plus 1 is equal to RK. So before adding and after adding. Okay, so how about EK plus 1 is equal to EK plus 1. Okay, how about EK plus 1 is equal to VK plus 1 as well. Okay, agree? Yeah. So remember, we want to show that R at the GK plus 1 stage follow this formula, right? Okay, so let's check. So RK plus 1 equals to RK by construction. And then RK is equal to what? So you are at the inductive hypothesis case, GK step. So you can apply the formula. RK is equal to EK minus VK plus 2. So this one is by inductive hypothesis. And then EK is equal to what? EK plus 1 minus 1 minus VK plus 1 minus 1. Use the above one also. So by construction is this part. Plus 2 construction. Okay. And then what you get is EK plus 1 minus 1 minus VK plus 1 plus 1 plus 2, which is EK plus 1 minus VK. Okay, so the formula holds. Okay, agree? Agree? Any question? Agree? Question? No question? No? Okay. So similarly, you can do for case 2. So case 2, what happened is your number of region increase, right? Because you produce an extra boundary, extra gate. Okay. So your region increase, right? So used to like connected, but you cut it. Okay, so you increase the region. Edges is also increased by 1. Okay. But vertex change or not? Vertex doesn't change, right? Because both of these vertex appear different. So you can see that actually this one here come to the number of region. Okay. So if you do the similar computation here, you will get the same result. Okay, then you'll get the same result. Yes or no? Okay, following? Still following, okay? Okay, good. So um so see this number 2 here, okay? So this number 2 here actually come from a small cases. And then from the small cases, you keep building up your graph, and then they still fall. Okay. So if you forgot the number, you can just straight away come back to this small cases and find the number. Yeah. Everything starts from this small cases. Of course, the planarity of the graph is very important. There's no like edge crossing. Then the number of region will like very complicated in that case. So that's why with this planarity of your graph, this formula holds. Okay. Any questions on the proof of the theorem? No. Okay. So from this theorem here, we have 3 corollary. Help us to identify what graph is non-planar. Okay. So corollary 1. So corollary 1 is if G is connected planar simple graph with E edges and D vertex, if D is greater than 3, then E is less than equal to 3V minus 6. Okay. And then the second corollary is if you have the connected panel, if you have a connected panel supergraph, then G must have a vertex of G not more than 1. Okay. And then corollary 3 is if you also got the connected panel again, with and also circuit of length 3, then it satisfies E less than equal to B. Okay, so how is it useful these three corollary here? So let me show you how to use it. So how we're gonna use it is we're gonna use it as a contrapositive. Okay. So if it doesn't satisfy this condition here, then it will be not planar. This is how we're gonna use this corollary here. Okay. Because what we interested in the graph is whether we want to know it is plan or not. Yeah. So this statement use the contrapositive of this statement. If this condition is not satisfied, then it will be not plan. Okay. So for example, in this case here, okay, let's show that K3 is not planar. So what's K3? Sorry, K5, sorry. What is K5? It's a complete graph with 5 vertices. So complete graph means you got 5 vertices, and then you join each vertex to one another. This is a this is the complete graph. So this is non-planar. Yeah. Okay. So how is it non-planar? So what's the number of V of K5? What's the number of V? 5. What's the number of E? The number of E. Huh? What? 20? 1, 2, 3, 4, 5. 1, 2, 3, 4, 10. Okay. So what is 3V minus 6? 3V minus 6 is 9. Okay. But 10 is greater than 9, which means 6. Okay. So this is not true. So this is not true. Okay. It is connected, it is simple, but it is non-planar. Okay, so this proves that this graph is non-planar. Okay. Okay. So this is one important non-planar graph you need to know. Later we'll see why this K5 is very important. Next one is to show that K33 is non-planar. Last week we already talked about K33 is non-planar using the planar representation. Try to find a planar representation, but we fail. So what's a K33? K33 is a complete bipartite graph. Okay. So you group three vertex on one side, and then you join them to each vertex. So this is the complete bipartite graph. Remember we showed this last time? Remember this? Maybe I just recall what we did last time. So this K33 here, okay, I try to find an isomorphism, okay, but when I try to place the last vertex here in three possible regions, we can't get rid of the edge crossing. Remember? Remember this one? Okay, so this one. And then today we use this theorem again, show that it is non-planar. Okay. So what is E? What is E for K33? What's the number of edges? What's the number of edges? 1, 2, 3, 4, 5, 6, 9, huh? 1, 2, 3, 4, 5, 6, yeah, 9. How about V? 6. So what's 2V minus 4? 8. But 9 is greater than 8. E is greater than 2V minus 4. Okay. So this is false. Okay. No circuit of length 3. Does this satisfy no circuit of length 3? What is circuit? So the path that start at end at the same point. Okay. This has no circuit of the length 3 because this is bipartite. Right? Because you cannot join these two edges with the these two vertex with an edge. Okay. So it doesn't has no circuit of length 3. It is connected. It is simple. Then there is only case is it is non-planar. Okay. Ultra positive of the corollary. Okay. So one thing you need to remember now is K5 and K33 is not planar. This will be important later. Any question? Do you want to see this proof or want to skip it? Or you can read yourself? Yeah. Expression. Uh-huh. You mean this one? Okay. You mean why what? Why I do like this? Okay. So last time, yeah, recall this last time we showed that K33 is non-planar. So I try to find a planar representation for this graph. Okay. So I try to find a representation that reduce the edge crossing. Okay. So first what I do is I take this edge and I move it down. Right? I take this edge and I move it down. Can see? Can see or not? Take this edge, move this down. So these three edges will follow. Okay, because graph isomorphism, right? What is connected before has to be connected after. Okay. So I take this edge and then I move it down. So it become like this. Okay, so this part here is still the part. Then here. Then the next part is I want to reduce this edge crossing. So there are three, I claim that there are three regions that I can put a, okay? I can put it outside here. I can put it in R3. I also can put it in R2. Okay. So my argument is if you put anywhere outside here, you can't avoid edge crossing. Okay. If you put inside R3 here, okay, you can reduce one edge crossing, but you can't avoid this edge crossing. Okay. And then if you put at R2, it is similar. maybe I add another picture then. Okay. Okay, so no matter how you place this vertex there, you can't avoid edge crossing. So there's no planar representation. Okay. So there are few ways to prove something is non-planar. One is to use this planar representation. I mean, try to find a planar representation, but you can't find it. So using the diagrammatic way. But when the graph is too big, then you can't really use this argument. So what you can do is what we did just now. You can go and check the number of edges and vertex. If it fails to follow the inequality here, then you can use the contrapositive of the position. Okay. So to show the graph is non-planar, one way is to explore the all explore all the possibilities. Then of getting a planar representation. Two, use the contrapositive of coloring. Okay, this one is a diagrammatic. And then this one is the count of edges and vertices. Yeah, two ways. Following, following. Okay. Yeah. Okay. Following. Okay. So actually, yeah. So next we're gonna talk about the third way. Yeah. So what's the third way? The third way is like the power of a topology. Talk about topology of a graph. So what we can play around with the graph is we can add a lot of edges into the graph. Okay? So we define a way to add edges into the graph, which we call the elementary subdivision. You subdivide your edges, and then I will show you the picture. So the picture is like this. Okay. So you got an edges, okay, U and V. What do you mean by subdivided? So you can add a vertex W, okay, and then you make this edge become a two edges, okay, and then you can keep going on. You can keep dividing it. Okay? This is called an elementary subdivision of a planar graph. So a precise statement is an elementary subdivision of a planar graph is done by removing an edge UV and new vertex W together with this, the two edges, like the U, W, and WV. And then you can keep doing, keep sub-elementary dividing. Okay? Okay, this one simple. And X, just cut it. Okay. Then the next part is we talk about two graph homeomorphic. Okay. So two graph. Last time we talked about isomorphism, right? So today we talk about homeomorphic. I'll give you example soon. So two graph is isomorphic if they can be obtained from the same graph. Okay. So just now I introduced one process, right? I must use this process. So how are you going to use this process? So if they can obtain from the same graph by a sequence of elementary subdivision. So mathematics is like this one. So when I introduce one thing, that's mean I need to use it later. I want to use it later and then keep going. Okay. So for example, okay. So last time we say that the K3, no, C3, the cycle or the triangle is not isomorphic to the square, right? You know why they are not isomorphic? Why these two are not isomorphic? It has to be bijection of what? Vertex. Okay. So why are these two are not isomorphic? You need bijection of vertex. So why this case is not isomorphic? Different number of vertex. Okay. So here is V equals 3. Here is V equals to 4. So you cannot have bijection on vertex, right? Because less than 3 is less than 4. Bijection need to be equal. Remember? Yeah. But the triangle is homeomorphic to square. And let's put this as homeomorphic, one line homeomorphic. Okay. Why is it homeomorphic? Because I can just subdivide one edge and then I get a square. Okay. That means all the cycle more than 3 are isomorphic to each other. Because I just keep subdividing. Okay. Then I will get the hexagon. Right. So I can just keep subdividing. This is homeomorphic. So you see, under topology, there's a lot of things that become the same. Not as restrictive as the isomorphism. Okay. So when you yeah, under subdivision, then a lot more things are considered the same thing. Okay. Any question to this one? No? No? Okay. So this one is a homeomorphism. Okay, next one. Okay, so here is the example from your textbook. So you got G1, you can keep subdividing your edges, okay? Subdividing the edges, subdividing edges, but 3 of them are homeomorphic. Okay, so you can simplify to this case. Okay. Actually you can keep simplifying, right? You can go to G0 by what? By this. Can see that or not? So you can go back to this one. Right? Subdivide these 2 points. Right? So you can subdivide it to become this one. Can see or not? Cannot see? Huh? Cannot see? I mean, so you can take this graph here, right? I mean, this edges here, and then you put A, and then put B here, right? So that you go to this one. I think this one is the simplest one. Can everyone see a formula of it? Color okay or not? Need to be darker. Can see this one can go into a simpler form. Can. So you can take this edge, add in A and B to become G1. Okay. Okay. So next theorem is, I think this one is the most powerful theorem now. So a graph is non-planar if and only if it contains a subgraph. Just now we only have if then statement, right? Now we have if and only if. Now if it is homeomorphic to K33 or K5. Okay. Just now we show that K33 and K5 are non-planar. So if and only if means if your graph is non-planar, then it must contain subgraph that is homeomorphic to K33 and K5. And if you found out that your graph has a subgraph which is homeomorphic to K33 and K5, your graph must be non-planar. So this one become one sole condition to check whether your graph is non-planar. Okay, so for example, my example picture. Oh, the picture here is here. Okay, so remember what's K5? The 5 vertex, the complete graph with 5 vertex. Okay, so every edges are connected to each other. So the claim is this G here is non-planar by the theorem because you have a subgraph that contains K5. So let me draw out the K5. Okay. 5. So 5 dot and then complete it. Okay. So you can see that actually this is not quite K5, right? Okay, because there is extra vertex here. Can see that? Okay, but never mind. We just need subgraph that is homeomorphic to K5. Okay, that means you can add extra dot here no matter how much dot you add. As long as you got this subgraph homeomorphic to K5, this thing is not planar. Okay, so you can see that you can reduce to a simpler graph which is already K5. Okay, can see that? Can see that? Can see that? Okay. And the G figure 14, maybe it's harder. You have to find that there's a K33 hiding inside this graph here. Okay, you need to do some manipulation, and then you will see that these 6 vertex here will build up the K33 inside this graph. Okay, so that means all the planar, non-planar graph must build up from K33 and K5. Okay, in some sense, these two are like the basic non-planar graph, and then everything else is just add on this K5 and K33. Okay. So all the planar graph starts from K33 and K5. Understand? Okay. So if your graph is non-planar, it must contain, or it is K33. Okay. 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 Any question up to here? Any questions? Questions? Any question? No? If no, then let's take a break till 10 o'clock. Then we'll come back from the spot.哎，
下周推测
应该下周
是14周，
14周。哎，对，
哦，那内容是什么？
那个partial ordering 啊，
这个 graph 环graph 是什么？那个 emo case 的那个
应该会比较简单，
要点，但是比其中简单很多。
比较简单，应该会比较直接。
就是不会像那么多基础的东西上加难度。
会再告诉你们啊，会再告诉你，会再告诉你。东进
啊？你没有听，你懂我在讲吗？
听懂了
啊？
听懂了？
你自己学习还是什么？
没有，
没有咩？
不是，我这个记了。
是咩？
我看你一直看下一页。哎，我在这边。我要给这看我的那个。不会就开头。哦，卡台是自己。啊，在工作啊。
啊
所以我忘记 K33 是什么意思。
，K33 就是你有3个 vertex 在下面，3个 vertex 在上面，3个 vertex 在下面，然后每一个 vertex 你都要连到
然后 K5 就是有5个 vertex，
6个 vertex 对，5个都要连到。
但是33的话是来上面下面都有。
哦，对，等一下，33的意思是说上面3个和下面3个都要连到，但是他们上面3个跟下面3个自己不用连。by part type。吃早餐啊？什么？哦。哦，好，可以，可以。 虽然它不跟地上日常可以足够让你至少你要时间放长一点哦，5个小时，我是上，但是我要那看出来也会学一下发展。一个小时，你不要说那个体脂肪还要在那里写，那个体量，可能比较多的应该是那个比较多的，比较多的。啊，因为好对，反正比较多的，是在一起，所以就更多了。Yes， 哎呀。Hello, testing, 1, 2. Alright, let's start. Let's start. Okay, let's start. Yeah, prepare yourself. Okay, before we leave the graph, last part is about graph coloring. Okay, so what's graph coloring? So there's one key question that we want to identify. So you must understand this key question, then we can proceed with this section here.
So what's the key question? I give you a map. Okay. I give you a map. So what's the least number of color that you need to color the adjacent region with different colors? So for example, if you color B with red, okay, because D and C and F share the same boundary, you don't color it as red already. So you color it as different color. So maybe you put red, blue, and so no adjacent region can have the same color. So what's the least number you need? So it turns out that if you regard the length here, again, this connected component here as a point, okay, string this length into a point, okay, string the length into the point, and then the boundary, you make it a line, okay. This is actually the question of coloring on the vertex of the graph. Everyone see it? Can everyone see it or not? So for example, in figure 1, if you string the length into a point, okay, and then you draw an edge whenever they share the same boundary, okay, so you make your edge into the boundary into an edge, then you can see that this graph here is actually the graph at the bottom. Everyone see it? Okay, so this become a question of coloring of vertex with different color on the adjacent. Okay. Actually, we encountered this before. This is the bipartite. How you determine the bipartite graph? Okay, if you can color adjacent vertex with 2 colors, right? Bipartite. Remember? Bipartite graph. Hello. Okay, remember. Remember. Okay. So bipartite graph, you can color adjacent vertex with 2 colors. That's a bipartite. Remember or not? Or I need to recall the statement. Okay. Okay. Recall. Recall. Okay, recall. So let's recall the statement. Let's recall the statement. Oh, which lecture is that? Forgot. What's the bipartite? This one. Okay. So a simple graph is bipartite if and only if it is possible to assign 1 or 2 different colors to each vertex of the graph so that no other 2 adjacent vertex are assigned with the same color. Okay. So you only use 2 color to color the graph. Okay. So because now our graph is no longer bipartite, so what's the minimum number you need to color adjacent vertexes with different color? Okay. So for bipartite, you can just use 2 color, but you can see that this one is not bipartite. Then you need to use more color. Okay. Bipartite, you just need 2 color to avoid adjacent vertex has the same color. Okay. So now we look at all the graph, every graph. What's the least number you need? The least number. What's the least number you need to color adjacent vertex with different color? Okay, everyone got the question yet? Got the question? Okay, then we can start tackling the question. Okay, so this question is very important before we start. Okay, so next. Okay, so before that, we can see this world graph, world map, and this is the world map. So how many color they use to color the map? Huh? How many colors? 3 colors? 4. Okay, good. 4. 4, right? Okay, the eyesight very good. So 1, 2. Okay, but some of them say 5 because got blue here. But never mind. This blue here actually can change, right? Okay, actually you can use 4. Okay, we will see this theorem. Okay, so why 4? Okay, so why 4 is enough to color a graph. So later we'll see a theorem. Okay, so next we define what's the coloring of a simple graph is. Okay, so we only allow colors that are different on adjacent vertex. This is what we call the coloring of a graph. Okay, we only color graph with different different color at different vertex. Because if you imagine you color the same color on all the region, then this map is hard to see, right? Isn't it hard to see the map? Yeah. Okay. So if we color with different color, then we can just based on the color we can see the region. We don't need to like look on the boundary. Okay. Okay. Why are you so happy? Okay. Okay. So yeah. So this coloring of edge is not allowed because adjacent have the same color. We only allow different color on the adjacent edges. Okay. And then next, we define the chromatic number. Okay. It's the least number of color that you need for the coloring. The number is called chromatic number. So chromatic number of a bipartite graph is what's the least number you can color bipartite graph? 2. So the chromatic number of a bipartite graph is 2. Okay. Which we write as a chi G. So for example, chi of a bipartite graph is 2. Okay. So next is the 4-color theorem. I think we won't prove this because the proof is out of the scope. So the chromatic number of a planar graph is no greater than 4. No greater than 4. So that's why just now we can color the map using 4 colors. Less than 4 colors. So showing to find chromatic number is important for this course. So strategy, how to find the chromatic number. Okay. So first you need to show that the graph can be colored with k numbers. So that means it is great. I think it's greater and equal to k. Right. So it is so you show that you have to use more than or equal to k numbers to color it. And then you need to show that it cannot be less than k, so which is equal to k. Okay. Okay. Cannot less than k, so it's equal to k. Think so. Huh? Okay. So you show that the graph can be colored with k colors. Okay. So it is less than equal to k. So wait, and then cannot be less than k. Here G cannot be less than K. How to write less than K? Okay. Did I do something wrong here? Cannot be fewer than K. So that's mean I think this one. Okay, let me ask you a question. So a graph cannot be colored using fewer than K. What does it mean? The chromatic number have to be greater or equal to K or less than equal to K. It up. Anyone look it up? So if a graph cannot be colored using fewer than K color, so the chromatic number is greater to K or less than equal to K. Which way? Which way? Which way? The graph cannot be colored using fewer than cannot be colored. So this one is the least number. Huh? Greater than equal to K. Okay, how about this one? Can be colored with K color. Okay, this one is less than equal because K is the least number, right? So every number have to be greater or equal to the least number, so that you can get all together you will get I is less than equal to K and then greater than K, which means I is equal. Okay. Okay. Confused. Confused. Okay. So the first one says that the graph can be colored with K colors. Okay. That means the chromatic number is less than equal to K because chromatic number is defined as the least number to color the graph. Okay. So every other number coloring have to be greater or equal to the least number. Can get the logic or not? Because you are the least number, right? So all other number have to be greater or equal to that number. Okay. Get this logic? Okay. The next one is the graph cannot be colored using fewer than K colors. So your least number must be at least bigger than K. Because if you go down K, then it's not enough to color your graph. That's why you get K is less than or equal to the I. So all together here, the chain here, you get the chromatic color is equal to K. Because this number is less than K and also greater than K. The only way is to get equal. Okay? Okay. Okay. Okay, let's see how to use this argument to find the chromatic number of the graph. Okay, let's look at G here. Okay, look at G here. So if I label A as black, okay, so the adjacent one should have the different color. Okay, different color. So if I label A as black, B as red, then C should be a different color than A and B. Okay, so we can put maybe green. Okay, but D is connected to B and C, so there should be a different color to both of these. Okay, we can either introduce new color or we can use back the all color black. Okay, because we want to use the least number to label our graph. Okay, so maybe we use black first. Okay, but can see that E is connected to B and D, so they have to be different color again. So one choice you can use is green. Okay, and then F is what? F is connected to D, E, and C. Okay, so one way we can use is red. Okay, and then G. Okay, agree the coloring rules. Okay, so that means we can use four. Okay, is it four? We can use three numbers to color our graph, okay? But if we remove one of the color, we cannot make sure that adjacent vertex have different color. So the chromatic number is 3. Can get it? Can get it? Okay. 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 How about this patch here? So let's label A as black, okay, B as red, and then C as green, and then similarly D black, E is what? Green, okay, and then F also red, G maybe black, okay. But you can see that this black here and this black here are connected, but they cannot be the same color, right? Okay. So the only way is to add another color in. Okay, so maybe add another purple. Okay, add a purple in. Then you can make sure that all adjacent vertex has the different color. Okay, that means this chromatic number is less than or equal to 4. Okay, less than 4. But if you remove one of the color, then the adjacent vertex must have same color. Either one vertex have to have the same color. Can follow or not? Can follow? Can follow? Okay. Okay, good. Oh, can follow. Okay. Oh, you believe or not? Or you want me to show you? Huh? You want me to show you? Or you okay? Huh? Okay. You want me to show you or not? No? You want me to show you? If I use less 3 number and then less than 4 number, you will get adjacent vertex that have a same color. You want me to show you or you are okay with it? Huh? Hello? Yes or no? Huh? Yes or no? Huh? Show show it. Okay. Okay, let's say we remove this you see, let's say we remove the green one. Okay, if we remove the green one, so this means there are only 3 choices here. One is red, one is purple, and then one is black. Okay, if you put black here, if you put okay, so if we remove 3, okay, so that means you have to put purple here, right? Okay, to avoid adjacent vertex have the same color. And then here you can put black again. Here you can put what? Purple again. And then here you can put red again. Okay. But there's only one way to put one color to put here, which is black. You can't avoid because you don't want the same color with E and F. But G have the same color of A. So less than 3 doesn't work. Can or not? No? Why? Why? Huh? Why? Can't. Less than 3 doesn't work, okay? Because you must have 2 vertex which are adjacent to each other, but they have the same color. Okay. Don't buy the argument. Don't buy the argument. Any question? Maybe the question from you is better. Question or no? No. Okay. If not, then we proceed. So we proceed. Okay, so the next example is the Kn example. So the complete graph. Okay. So the claim is the chromatic number of Kn is 5. Okay. No, sorry, K is 5. It's n. So depend on the vertex of your the graph. Okay. Remember that how Kn is constructed. You have n vertex, and then every vertex are connected to each other. Okay. So this means if you put one color, if you put one color on one edges, okay, all the other edges must have the different color because they are all connected. Okay. And then the claim is n color is enough to color your vertex. Okay. So, okay, one question for you. One question for you. So does this break the 4-color theorem? Because 4 colors theorem says that the chromatic number of a planar graph is no greater than 4. But if we take K5, it is 5. Does this break the theorem or not? Huh? Sorry? Okay, it must be planar graphs, then you can use the 4-color theorem. So that means K5 is not planar. Okay, another way to show it is not planar. Okay, so there are 4 ways to show something is not planar. Okay, okay, next. The bipartite graph, we already encountered this KMN. It's always 2 bipartite. You can always use 2 color to color bipartite graph because you got the bipartition of vertex, one group, one color, one group, one color. Okay, 3. The cycle graph. Okay, cycle graph. If you look at the triangle here, okay, how many color you need? You need 3. 1, 2, 3. Okay. How about C4? C4 you can put 2 is enough because you can see that only the degree of the vertex is 2. Okay. But the problem with the odd number is you will have 2 extra vertex that have the same color if you do this alternating coloring. So that's why you got a +1 chromatic number than the even case. Okay. So it is 2 when your vertex is even, and then it is 3 when the vertex is odd. You can try it for C6, C7, then you can see the pattern popping up. And then you should be able to write out a general statement to say why the chromatic number is 2 when the number of vertex is even, and then 3 when the number of vertex is odd. Okay. Try and color it yourself. You know what is C6? The hexagon. Then you keep adding 1 edges and then do the coloring. Okay. Okay. So what's the application for this? You can use it to schedule your final exam. So it's like if you got 4 exams, right? So you are all the 4 exams connected to you. So make sure the 4 exams are not color as the same. So you put all the same color in one day. If different color in the same days, then you split yourself. Split into half. Yeah. Okay. Yesterday, they asked about one question. Okay, out of textbook and out of box one. So they asked about wheels. Okay, what's the chromatic number of wheels? What is wheels? So you got a cycle and then you add 1 dot in the middle and then connect the dot to all the other vertex. So this is the W W3, W4, W5, and W6. Okay, you got a cycle and then add one dot, like the tires. Okay, so the claim is the chromatic. So we conjecture that the chromatic number of the wheels is 4 if n is odd, and 3 if n is even. You can try and show this. Okay, so we try to color wheel 3, and then wheel 4, and then wheel 5, and then wheel 6. Okay, so the claim is the chromatic number of wheel is 4 if n is odd, if 3 is 3 if n is even. Okay, this is what we conjecture is the way. You can try and show it. Yes. You mean this one? Oh, it is less than equal to 4 because we use 4 number to color it. Okay. But pi W3 is the least number, right? So this least number must be less than or equal to this number. The same logic just now we talked about. Yeah. What? What do you mean only 4? Yeah. If we combine these two, we get equal to 4. Yes. It must be greater than equal to 4 because if we remove either one of the color, you can see that the adjacent vertex must have the same color. Okay, let's say if we remove the yellow color, okay, if we put green, if we put white here, then it will violet here. If I put red here, it will violet here. If I put green here, it will violet with green. Okay, so you must have at least 4. Less than 4, less than equal to 4, greater than equal to 4. So it is equal to 4. Okay, and then you do it for different cases, and then you should come up with a general statement, general argument, talking about how they connect, and then you can prove that this is true. This is conjecture, haven't proved yet, so you can try and prove it. So if you prove it, then you can put your name. Actually, this one I think someone proved it before. Any question? Yeah, this is exactly our process. Come up with a conjecture. So we go and compute a few examples, and then we see the pattern popping up, and then we see some pattern going on in the graph, and then we try to prove it. You can try and prove it. Okay. A question on this graph coloring chromatic number. No. No. Proceed. Okay. Okay. Next, we'll talk about trees. Okay. What can appear in your mind is you can think of coconut tree, banana tree, durian trees. Okay. So what are trees in the graph? So we don't want to have simple circuit in our graph. Okay. Do you see the leaf that can grow back to the stem? No, right? Okay. So this is tree. So you can see this like trees. Okay. So it's a connected. So it's connected graph. So there's nothing like disconnected thing. So there's only one connected component. And they're connected, undirected, okay, with no simple circuit. Okay, trees, something like this. And then this is not a tree because you got a circuit. Okay, we don't look at this thing. We just look at something like this. Okay, trees. Okay, next we will introduce a bunch of terminology. But before that, from this definition here, we can see that an undirected graph is a tree if and only if there exists a simple path between any two vertexes. Okay? So meaning if you pick any two vertex, there's only one way to get to it. There's only one way. There's only one way to get to it. One simple path. Okay. So in the tree, there's only one way to get between two paths. You can prove this directly from the definition. You can look at the textbook as well for the proof. Okay, the next one is rooted tree. So rooted trees, we pick one vertex and we call it a root. Okay. And then all the other part, we will make it directed away from the root. Okay, what do we mean by that? So let's say if we take this trees here, okay, and then if we pick B as a root, okay, B as a root, this means you try to leave this B out. Okay. So you can see that E, A, C, D will like directed away from B. And D is the furthest away from D because the length of path is more than the other, for example, E and A from B. Okay. So you can think that when you leave out B and then the other vertex will fall. Imagine this vertex has weight, so they will fall using gravity. Okay. Trees. Okay. So if I pick my root as C, so I will lift this point up, and then all the other point will get directed away from C. Okay. Rooted trees. And answer. Okay. Okay, next, there's some terminology here. So this tree is like your, okay, what's the word? Genealogy. Genealogy. So we will use word from terminology from genealogy. So if it is not a root, okay, we'll call a parent of a vertex if there's a unique vertex that's connect from the vertex called the parent. For example, E. What's the unique vertex that connect to E? Okay, in this case here, is B. So B is the parent of E. Okay. So what's the parent of A? Okay, parent of A is B. Okay. Is the unique vertex that you connect to you. And it is not a root. Okay. I mean, roots doesn't have a parents, but all the rest has a parent. Okay. And okay, next. So when U is a parent of V, then V is a child of U. Okay. So for example, B is a parent of E, and then E is a child of B. Okay. And E and A has the same parents, so they are the siblings. Okay, siblings. And then the next one is ancestor. So what's ancestor? So ancestor are all the edges that is above U that are connected by an edge. So for example, E. Who are the ancestor of E? B and C. Okay, all the way up. So what's the ancestor of A, E, and B and C? Okay. Next is descendant. Okay, descendant. So descendant means for example, descendant of C is all the points that have C as the ascendant. Okay, so for example, descendant of C is B because C is the parent of B. Descendants of C is E because C is the ancestor of E. Okay, so all the way down is the descendant. Make sense? Make sense. Okay. Okay, and then the vertex of a root that doesn't have a child, doesn't have children, is called a leaf. Okay, so these guys are the leaf. So for example, in this rooted tree here, E, A, D is a leaf because they don't have child. Okay. In the rooted B trees here, E, A, D are the leaf because they have no children. Okay. So leaf is the terminal vertex. Okay. And then the vertexes that have children are called the internal vertex. Okay. So if you are not leaf, then you must have a children. So these are the internal vertex. So that means internal vertex and leaf partition the vertex set. Make sense? So if you cannot have child and you don't have child at the same time, right? So if you don't have child, you are a leaf. If you have a child, you are an internal vertex. So these two sets partitions your vertex set. So you are either an internal vertex or you are a leaf. Okay, can get it? Okay. So this one partition the set. Okay, next one is a subtree. Okay, so what's a subtree is? First of all, it's a subgraph. Okay, and then second of all, you must contain a subtree with a root A. You must contain all the descendant of A. Okay, so for example, so let's look at maybe look at here again. So what's the subgraph of subtrees rooted at B? Okay, so you need to start from B. Okay, and all the descendant you need to include. Okay, so for example, if you just draw like this, B and E, okay, this is a subgraph, but it is not a subtree because you don't include all the descendants of B. Okay, so this is a subgraph, but not. Okay, so subtree you need to include all the descendants. Okay, make sense? Make sense? You need to include all the descendants. Yeah. Okay. Okay. So in a summary, let's check this example again. So ancestor of E, yeah, is B and C. Okay, in this rooted tree, and the parent of E and A is B, and then E and A are siblings. E and A are also child of B. Okay, and then what is after C? For example, B, D, A, and E are the descendant of C. Okay, and then E, A, D is a leaf. B, C are internal vertexes. Okay, so you can see the internal vertexes and the leaf partition your vertex set. And then the subtree that you draw at B is something like this. Okay, subtree rooted at C is the whole thing. Okay, you should draw the whole thing. Okay, so these are the some terminology for trees. Okay. Maybe we don't get into algorithm today. Maybe next week we'll do algorithm on trees. Okay. So far, any question on this terminology? I think quite straightforward, right? Okay. Any question? Just some terminology before we haven't get into the real subject, but we will do it next week. Any question? No? Okay, if no, maybe we'll take break until 10:55, and then one by one you I forget to pass down this attendance list again. One by one you can come get your quiz. Oh, last quiz sheet. We'll discuss quiz 3. Okay. You can come collect your yeah. Okay, take a break until 10:55. Stop了。Stop了。啊？可以加分到10分，最多。哎，啊，
只要超过10分就可以。
对。
哦，
我要
要是10分就是满分。
啊，10分是吗？不能够拿
更多分
啊，
一共16分。
Yeah，送超过半分了。没有你的记忆啊。
那之前同学也好聊哦，我自己
出自己的牌子。怎么？
没有只要3了，对，应该是5。
可是你这边算出来是5的东西。
啊，是吗？
没有没有，我问你。
啊，3来的。
是咯。怎样？1分半了。
对。
你没有 bonus mark 吗？
怎么办？
你 bonus mark
没有错的。1分吧。
1分半。
1分钟。
OK。You haven't got it? You haven't found yours? Okay. Here. This one? Oh, your friend. Your friend. 这个你全部整齐，你看一下是不是？
这是
这样。感觉不知道你在写什么。
就是 flexible，
reflexive 是 XX 哦，为什么变成 XFX 啊？
因为就是 x 等于 fx 啊。就是不太表达。x 是 x，
因为你没有它的逻辑是，等一下我讨论一下，然后讨论一下，大家看一下。哎，
这理解那个 root 的去
什么
叫 root
root tree 啊？怎么说？怎么说
不是理解。
？root tree 就是你选一个 vertex 当成你的 root，OK，然后你把它当做其实所有的点都向它延伸，这是 direct 呀。
我感觉
就是你想象一下这个 D 不是它有一个，你把它提起来，然后其他的点都有重量，然后它会往下。
去的基本定义不都应该是这样的，难道有特一个点出来？
你说 tree 上
对，
没有啊？你看这个 tree 上，你看这个 tree，你看这个 tree，这 tree 怎么说是从一个点出来的
哦，就是它
？tree 只是要你 connect， 然后没有 simple circuit， 但 tree 我们就让它有一个起始。
挺快记，
什么问题？
是那个那个是
哦，chromatic 哈，chromatic number。
它一开始是讲一个图色，
对对对对对
点
啊，对对对对对，因为我们把这个图形啊想成是一个点，你看这整片把它想成一个点，把它缩成一个点，
对啊，
缩成一个点过后，这些边啊就变成线哦，只要它们有共享一个边的话，我们就画一条线；共享一个边，我们就画一条线；共享一个边，嗯，然后你就可以看一下这个，其实就是这一个 graph。
如果你通话，你看你就三单任何几张嘛，然后也去懂。
13张选一张，然后12张选一张，然后1张选一张。第13可以投，第13不一定吧。13张，
因为
3张选一张，然后剩下12张再比。
郭宏林听到吗？郭宏林，郭宏林，昨天04层。林轩有，林轩有，林轩有，林轩有。大云轩，王董，王董，王董， Oh. On top. Ko Hong Ling not here. Ko Hong Ling. Ling Xuan Yu. Hey, who's friend of Ling Xuan Yu? Anyone is a friend of Ling Xuan Yu? Who know Ling Xuan Yu? 你是林泉佑啊？林泉佑哎，不懂。郭宏林哎 ，Who's friends of 郭宏林 ？Who knows 郭宏林？郭宏林 ，No one know 郭宏林，女生来的，那女生。Okay. Is everyone back yet? Okay, I want to know before we discuss. How many of you play this Cholai before? Can I see how many of you know Cholai? Okay. Because this quiz, your class first time is the highest average mark. Final 出了没？ Okay. Okay, let's come back. Okay, so this question, I put a strategy game. So there are a few combination of cards, and then we see how many combinations are there. So question 1.1 here, how many combination of picking 5 cards from the deck? Okay, so there's no condition on the card. Okay, so 52 cards altogether, just pick 5. Okay, so this is all the possibilities you have. We don't care about arrangement, okay? We just care about combination. So we just use choose. And then 1.2. So 1.2 is asking about straight flush. Okay, so what straight flush is? 5 cards sequential in rank. Okay, rank is 2 to A, 2, 3, 4, 5, 6 until A. And then 5 cards in sequence. And then all have the same suit. Okay, same, or we say flower, same suit. So there's only 10 possible sequence, and then there's only 4 kinds of suit. So it's 4 times 10. Okay, I don't care how you get the 10 sequence, but there's only one way to get it. So there's only 10 ways. And then each sequence you have one kind of color, one kind of suit. Okay, so it's 4 times 10. 1.3. 1.3 is flush. So what's flush? Okay, just now it's straight flush. Now it's flush. Flush means 5 cards with the same suit, but not straight flushes. Okay, so there's some there's a inclusion exclusion principle here. So only requirement is same suit, but there's no condition on the ranks. So it's 4 times 13 choose 5, because you need to pick your 13. You need to pick the 13 number from the same suit and then choose 5 of them. Okay, and then there are 4 suits, so 4 times 13 choose 5. But the question said not including straight flushes, so you need to take away 1.2. Okay, inclusion exclusion principle. Okay. Okay, so 1.4 here. 1.4 bonus mark. 1.4 bonus mark here. Let me check something. So if you do the bonus mark, but your marks is not full yet, then this bonus mark will help to add your mark until maximum. Okay, so bonus mark here, four of a kind. Four of kinds consists of all four cards, okay, of one rank. Okay, so the rank have to be the same. Four cards with the same rank plus one additional random card. Okay. So it's 13 times 48. Because 48 is after you take away the four cards. Okay. And see so I think the picture to have in your mind is something like 2, 2, 2, 2, and then random. Okay. So there's only one way to pick 2, 2, 2, 2. Okay, and there's a 13 rank of them. Okay, and then pair have and then this extra one is 52 minus 4. And then full house consists of pair and three of a kind. So in your mind you should have like 3, 3, 3, 2, 2. Okay, so there's 13 way to pick the three of a kind, and then you left with choice to pick the pairs. And then in the three of a kind, you can choose 4, choose 3, or choose 3 because you can have either 3 suit, and then 4 choose 2, either 2 suit for the pair. Okay. One controlling the rank, one controlling the suit. Okay. And then a straight. Okay, a straight is a 5-part sequence in rank, but not all 5 with the same suit. So there's some exclusion principle coming again. So it's a 10 sequence, okay? But you can have different suit. So inside each sequence, all the number, you have 4 possibilities. Okay, let me draw something else. 4, 5, 6, 7, 8, 9. So in every step, you have 4 suit to consider. Okay, so that's why 4 to the power 5. Okay, times 10 because you got 10 kind of sequence, and then take away your straight flush. Take away 1.2 again. Okay. Yeah. Any question on question 1? Which part you want me to repeat again? Yep. 1.2 want me to repeat. Why? Why just 10 times 4? What do you think if it is not 40 C5 40 C5 40 C5? So can you explain why you want to take 40 C5? Why you take 40 C5? 40 is what? 40 is the total number of straight flush. Oh, wait. So, what? No, the question is asking you to find the number of straight flush, right? So, why is it 40 C5? Why is it 10 by 4? Okay. Because there's only 10 way you can get the straight. Okay. And then 4 is because each straight you have either what? You have either diamond, club, heart, or spade. See? Let you think. So if you got a string, for example, A, 2, 3, 4, 5, okay, so they are either diamond, either heart, or either. Okay, so 10 possibility here, 4 possibility here. So all together. Okay. 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 There are like 4 persons score my bonus mark. Oh, Yifei is one of them. Shang Haoru, who is Shang Haoru? Oh, okay. Yeah, Shang Haoru. And then Chung Wai, and then Zijian also. Score the full bonus mark. Okay, next one is the relation. Okay, relation. 2.1 is my lecture example. If you don't know how to do, that's mean you don't study the lecture notes well. Okay, so the function is fx equal to x for all x. Okay, it doesn't matter what set you take. It doesn't matter what set you take, but if you draw out the graph, I think you should mean the set is real. Okay, so what is reflexive property? So how to earn these 2 marks here? So first you need to tell me what is reflexive property. Okay, so reflexive property is for all x in the set, x has to be in the relation. Okay. But your relation is x fx. Okay. So that means x fx is in the relation. So these two are equal. That means fx has to be equal to x. Okay. So maybe let me write something more so that you know what I'm doing. So let me write x fx x is in the relation. If and only if and only if what f is function of x. Okay, and then things things. Okay, let me write more things so that you know what I'm doing. Things x is in R for all x in the set, and for all x in. And then I think some of you confused with the real number and the relation. Okay, so be careful when you write this relation and the real number. Be careful when you write the okay. So these two have to be equal, right? So order pair x has to be equal to x has to be equal to fx. So you get the fx equal to x. Okay. Okay, so this open-ended question, I'll give mark as long as you follow the example. So meaning If you want to say human relationship is reflexive, then you have to say that for all, everyone, for example, okay, let me give some argument here. So maybe my answer, okay, my answer. So if I say that human, okay, I put HR already, HR. So HR is reflexive because everyone know themselves. Okay, because everyone know themselves well. Everyone know themselves. Maybe if I say HR is not reflexive because someone don't know themselves. Not everyone know themselves. Know themselves well. Okay. Two, HR is symmetric. I think most of you say, if I treat you well, you will treat me well also. Okay. Okay. I cannot say it's not true. This is your belief, right? So I think it's a good belief. You should keep continue believing. And hopefully others will get influenced as well. So what else? I remember what kind of example. Yeah. Transitive. I think one of you quite interesting. So you say, so husband is good with the wife, but the wife is good with another with the another guy. But the guy with don't won't be good with the husband. Right? Okay. Yeah, something like that. So in the whatever you wrote is if you want to show reflexive, symmetric, and transitive, you need to show for all cases. If you want to show they are not, you just need to produce one case is enough. Okay. 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 Or any one of you got interesting, you think your example is interesting, you want to share. Huh? Okay. Anything on the quiz you want to ask? On the quiz you want to ask? No? If not, you can start on the tutorial question. If you want to ask about your mark, you can. Yeah.
Super。用它的这个1.4这个
OK。
因为就是说写到最后它没地方放。
你没有改到啊？
然后这
OK OK OK。所以你是对咯，你对完是吗？
我没有改。
我看一下你的分数啊，你是106。106。OK OK OK，可以。 所以是满分呢？满分呢？1、2、3、4、5、6对吗？所以满分10分咯。来，我改一下。过去了，又还给我。好，OK。呀，
就是想说
，x
x f(x) 啊，然后因为它这个等于这个，所以说 x 逗 x 也是。
好难去，好难去。但是你没有解释什么是 reflexive。
就是两个类型相等就。
你应该要写这个，x，你这个没有标记你的这个活在哪里这些东西，
什么意思？
就是你没有标记这个东西活在哪里。
活？什么活？
就是它在什么 set 里面。
哦，
因为如果它在不同 set 里面，它不长成这样。
直接这样写就可以吧？就是我想表达意思是，这个东西属于 R，然后因为 x 等于 f(x)，那么 x 也属于 R。
对呀，你没写出来啊，问题是
就是
你没写出来，问题是没写出来。
它已经就是相当于代换嘛，这不是一个。
没有，你要写出来，重点是你知道的东西要把它写出来，不可以叫人家去猜啊。要写的几分？几分？
我看8分。
8分。
这个前面的
可以再给1分啊，要写出来就是。
前面的那些没给过程的，这种就是
你算的是对的嘛？你算的对，我才可以给分。
就是中间有一写错了就不行。
应该这个错就是错了。
就是比如说这个把
哦，可能你有减这个减对的话啊，OK，可以，我讲一下，Hello，testing，1 2 testing 1 2 OK。One additional point here. So let's say if you don't compute this number right, but you take the right subtraction, I'll give you mark. Let's go. so if you apply the right principle of inclusion as exclusion, I will give you 1 mark, even though if you compute wrong here. Okay. If you use the right inclusion and exclusion principle, I'll give you 1 mark. 所以你是说这个错，这个对是吧？可以给1分了。
加
1分，这个你下次要写完整的，1分2分，加2分。说你是102，这个4分，然后这个是这个4分。等一下，OK，这边变成10分，OK，可以啊，这个还给我，
我做一下对，
大家看这个 OK，可以，就这个吧。
这个吧，3分。
8分。OK，所以没有做 bonus 吗？
多少错？
哦，做。
是前面那个对耶，
那个前面那个对，就这个加一。对，好，等一下啊，你等一下啊，你前面那个对，给我看一下你怎么来1.3的，这是什么？哦，你前面那个对，你没有拿掉那个啊？对，给你1分。OK，你是 electronic 啊，你是上网考啊？啊，对对对，我记得940，8分啊。OK，对，1分的。哦耶0831杯，这哈是啊，OK，满了啊。好，这个诶，这个你不要，这个还要吗？拍吗？来拍，OK OK，好，OK，一个吧，one this one，OK，哦，加分，哦，加9分，对，OK，这个你不要了啊，OK，好，来，
就为了这一分。
OK，可以。啊，最上面 OK，6分，
那场
很大，没有做 bonus，没有 try 一下 bonus。OK 啊，
为什么我这个生错？
哪个字？
就1.3这个，我是先52张牌里选一个，然后在它同种花色的12张牌里选4个跟它比对。
1.3，你说1.3，
对，1.3。
12个里面选一个，
它不是要数字，
就13哈，这个13，只要同花，same 数，为什么12个选一个？
就是我先随便选一张牌，然后再选一个跟它相匹配的。
哦，
这是什么？
数是花，
对啊，
难道你要选 C？
就12先选一张，剩下是跟它同种花色的有12张牌，我12张里随便选4张，
没有错，然后
但是
你算一下，算一下这个号码跟这个号码一样吗？
好像不一样。
不一样啊，不一样啊，你这个乘出来跟我这个乘出来不一样。
好像多了不少。
多了不少。OK，这个减呢，我可以给你加分减，因为你减掉这个1.3，多了。
不知道为什么。
这个呢？不算多了。
这么多人吃
有做那个。嗯，算多了，可能我要想一下，我想一下
这不对，这是期要算的。
啊，你在计算机上面。OK， only one。OK。Why can't I find the 222? Why not 222?
Here.
Where? 822 eh? That is 222. Okay. You don't need this? OK。
That's right.
That's all. Okay.
So I cannot. I didn't minus the 40, but the front part correct.
Oh, the front part correct.
Yeah.
Okay.
Thank you.
Nice.
Yeah, thank you, sir.
Okay. Hey. Yeah.
OK，
来，
他的表演。
这样。
哦，
哦，OK。
不是你，然后这个
哪里？
这两个哦，我的那个 concept 是对的，只是那个乘变成加，好不好？是
难哦。
就是如果我那时候我就忘记它是乘还是加，然后是它那个一样的啊，是我忘记那个地方要写乘还是加，然后我还把它理掉，原本是对的，
原本这个是对的。
可以一点同情的分数。
给我看一下先是几分啊？95。那个哈，
对，
那个要挖它。
是的，你忘记了，就是混的呀，我都
OK。
可怜了。
知道为什么要乘吗
我知道我一做完我问出来，哇，这个，
？OK。
所以我 concept 不是很 clear 的，有那个酸的那个，我懂是什么酸，
对呀。
那就没有，所以就不会了。
OK。一分呢
所以
？OK。
谢谢你，
quiz 可以松一点。OK。
谢谢你。
哎，这个好啊。
它本来是 x 不是，可是我提升了。
OK，然后
都可以嘛。然后我的那个其实是 x 等于 x 的时候，它 x 也是等于 x 嘛。然后我写成这样子，可是我 proof 的时候写这样子的，可以给一
没有嘞 reflexive 那也是这个意思哦。
啊
reflexive 是 x 要在那个 relation 里面。
然后它是 f(x) 不是
啊 x 没有，因为这个是 reflexive， 然后你的 relation 是长成这样。OK， 所以这两个要等于，的话，意思说这里要等于，这里也要等于，
要等于两边啊，
对，所以你才会找到这个等级 fx 等于 x。
要等于一边。
一边嘛。我们重点是要这个 fx 等于 x， 这边肯定等于这边。
可是这边这个我写的是 y， 可是
对，我知道，
对吧？
但是你没有真的写到这个 reflexive 的那个啊，对 ，reflexive 不是这个意思。
所以如果我写 x 等于 fx， 然后后面都把它列就可以了。
你可以写 if x 等于 fx， 对，或 x then x then xx 就 then x fx 等于 xx 就会在 relation 里面。然后这一个才是 reflective， 对，等于的话不是 reflective， 可以吗？这两个在 relation 里面才是 OK， 可以啊
OK，
可以啊。
对。
其他没有啊？
老师，我这里全部没回声了，我吐死了。
什么？这边说完？
没有，
哦，用到 P。
我以为是要 permutation，
他不讲 combination 啊，
你没有看到吗？
那时候做完之后，那个牌456
啊，
就是他以为
可以可以这换，结果错了。
换来换去都是一样的东西。
那可是 I mean 我的接下来我以为可以4、5、6、7，1、2、3、4、5，然后还有一个是3这样子
啊
3、4、5
啊
那个错了。
，OK，
那个是
什么东西啊？
就是考试一坑的 scale。
那现在有一个暂时的总分吗？加权的。
我还没跟他弄出来，我还没把它做出来，快一点要把它做出来。
我们期末老师你也会像期中一样加权吗？
为什么？
就是不是期中你是乘70%？
哦，期末应该不会啊，期末比较简单，应该不会。
期末真的比较简单。
那你期末的那个题目不会像期中一样那么多？哦，
会减少。
老师我
来，
你看这个题的话，是因为我没有看到这个 set
点
然后这个题还有2分，就是我只有这里没有看到，但是我的思路就是10是乘它有这种10个牌嘛，
对，
4它就是花色，因为我没有看到这次，所以我就乘了5次，
对。
然后我就可不可以回分，就是思路是对的，就是没有。
但是你思路是对其他题目，不是对这题。
就是我这里只没有看到这个，
我知道。
然后它有2分，对不对？
我知道。不行哎，除非你把这个东西搬去这里用，厉害一点，放在这里用，这个放在这里。如果你再重复这题用这个的话，哎，这里有分啊，哎呀，
然后这一个题的话，它不是要有2个步骤吗？我没有看懂题，但是这个算一半，是不是？它有2分就可以拿1分。
哪里有算一半的东西？
那好，这不是步骤分吗？
没有啊，步骤你都没有，就 OK
狡辩了，挣扎了一下。
OK 没事没事，对，
我想看一下那个贵妃的。
对，
呢，它是不是全部都已经封顶了呀？
哪个？哦，对，这个有加分，你忘记扣啊？不是，你忘记把那个啊，对，OK 好，3是607。是，好 ，OK，哎，看一下，480哈，OK，没问题，
这个是10乘4跑5嘞，
因为每一个 sequence 都有4个花，
然后
每一个都可以不同花，就是你就可以 diamond，这边有4种花，这边有4种花，这边有4种花，这边有4种花，这边有4种花，每种不同。给他，
我给不到。
你解释给他听。
你要一样的色，
Hello，来，what？还有吗？Can discuss tutorial question at 10:11:35.
我觉得只有这4分之2答案是比
1.4呢？哦，对，就这个啊。对，然后10分。we will discuss the tutorial question in
minute. Everyone sign the attendance please already.什么故事这样好听那边？还有什么故事这样好听？没有讲那里有什么故事这样好听？熊爱上个礼拜没有来，还听得懂啊？啊，听不懂啊？OK。Okay, so maybe just go through some question here. So 10.4.2, you are given four path, given four, how to say, sequence of vertex, and then check whether it's a path or not. Okay, you don't know whether it's a path or not, so you check whether it's a path or not. So A, B, E, C, D, A, B, E, C, B is what? A, B, E, C. Why stuck already? Okay, C correct. A, B, C, B. Okay, is a simple path. Okay, of length 4 because you can combine them. AD, A, D, A, D, A. A. Okay, AD, AD. A. No. A, D. D, okay, correct. AD, AD. Okay. Okay, this one is a circuit because you start at N at the same point, but it is not a simple circuit because you repeat AD and DA. Okay. Next is A and then D and then B. So there's no H here, so cannot combine. So it's not a path. Similarly for D. Okay. 10.4.4. Okay, I think it's a graph. You should look at the graph and then you should determine whether the graph is connected or not by looking pair of vertex. I don't have the picture here. I think there's a picture in your graph. And then you just take two vertex and then see you can find path with them. If you can find it, then you can. Yes. 10.5.2. Yeah, find an Euler circuit. So first of all, you need to determine whether a path, a graph got an Euler circuit or not. What's the theorem? All vertex has to have even degree. So you need to count whether you got even degree or not. And then you got an Euler circuit and then try to construct one. Okay. After you determine that every degree have even degree, okay, then you try and construct one Euler circuit. Okay. Euler circuit is not unique, so there may be more than one. Okay, Euler path. How to determine whether you have Euler path or not? That's an if and only if statement. First, how to determine? There are exactly two vertex with three. Exactly two vertex with what? odd or even degree? Odd, because the 2 is the starting and the ending point. So if your vertex all have even, then you can't have odd degree, right? So you don't have Euler path. So if you have Euler circuit, you cannot have Euler path. Okay. So 10.5.4 also the same. And then use check whether you got Euler circuit or not, because not all even, no Euler circuit. Why got Euler path? Because you have exactly 2 vertex with the odd degree, and then these 2 odd degree is where C and F. Okay, so C and F become your starting and your ending Euler path, and then you can go whatever where you want and then come back. Okay, depend on the graph. Okay, so must know how to determine you got Euler circuit, Euler path. No. 10.5.6 also the same. You can see that B and C has odd degree. So B and C become B and C become your starting and the ending. Okay, so the middle one you have to use your creativity. Okay, so how to build the middle path, you need to use your creativity. But you know where to start, where to end. Yeah. Okay. 10.5.8. Also same. Okay. Give you a graph, ask you whether got Euler circuit, Euler path or not. So go and check the degree. Okay, we found that all the degree are even. So you have a Euler circuit. So use your creativity to build your own Euler circuit. 10.5.10. Okay, this one, huh? Okay, this one is another 1, 2, 3, 4, 5, 6. This one is 6 bridge problem. So you make it into a graph problem. Okay. And then you check that every vertex have even degree. So you got an Euler circuit. Okay. Okay, since we talked about this, right? Actually, I found 7 bridge problem, Putrajaya. Yeah. Okay, I found this Putrajaya 7 bridge problem. You see, yeah? But this one is a different 7 bridge problem. How many bridge to Putrajaya? 1, 2, 3, 4, 5, 6, 7. Okay, 7 bridge to Putrajaya. So the question is there an Euler circuit on the Putrajaya? Any Euler circuit on Putrajaya? No. Chumai say no. Why? Why Chumai? Huh? Why is there no Euler circuit on Putrajaya? Huh? Do you know? Why? Why no Euler circuit on Putrajaya? Anyone got any idea? I can give you about 2 minutes to think. Everyone know where is Putrajaya or not? It's the government administration office. Quite nice. You can go and visit Putrajaya. All the money go into Putrajaya. All the money go into decorating Putrajaya. So the country become again. Why? Okay, got answer or not? Why there's no Euler circuit on Putrajaya? Answer why no circuit on Putrajaya?
Which one?
Which part is connected? Very good. So which part is connected? So yeah, so you need to determine which part is connected, right? So actually, the whole part here is connected, and then the inner part is connected. Okay, so there's only 2 vertex. Two vertex between these, so it's like either Putrajaya or outside Putrajaya. Okay. And then Putrajaya and outside Putrajaya is connected by 7 bridge. So what's the degree of the bridge? What's the degree of the vertex? Huh? Odd. Okay. So the degree of the vertex is vertexes is odd. Okay. So odd, no Euler circuit. But there are two exactly odd numbers, so there's a Euler path. Okay. So you got Euler path, but you don't have Euler circuit. You can pass through all the bridges at once, but you cannot come back to the same point. Okay. So yeah. So if you walk, that's mean if you walk all the bridges at once, either you end up at outside of Putrajaya or either you end up inside the Putrajaya. Yeah. Okay. Okay. Yeah. Okay. Next, Hamilton circuit don't have not as systematic as Euler path or Euler circuit. So Hamilton circuit sometimes you need to try. For 10.5.30, there's no Hamilton circuit, okay? Because for all the circuit, you need to pass through this, the middle edge twice. 5.32 have no Euler's Hamilton circuit because you got one vertex of degree 1. Okay. Because when you go in, you need to come out. Or if you go out, you need to come in. So you need to intersect E twice. Again, same argument as the lecture notes. 10.5.34. No Hamilton circuit. This one is harder. You can see that if you have a Hamilton circuit, those degree 2 part, those degree 2 vertex, all the edges you need to include. And then you can't avoid passing some of the vertex twice. 10.5.36. You have a Hamilton circuit, just produce one. Similarly, for 10.5.38, produce one. 7.2.4, this one shows a graph is planar. Produce a planar representation. Again, try to play around with the edge and the vertex. Okay. Vertex jump away. Try to move this vertex or edge away. Then you can find some representation which has no edge crossing. See, I move the edge crossing outside. I move the edge crossing outside. Okay. Such that they don't have edge crossing. Then these two graph is planar. Okay. They are isomorphic graph. Planar is no edge crossing. There's no edge crossing intersection. Okay. And before you leave, give me back your quiz. Okay. That's all if you don't have any more questions.